Welcome to our presentation on mastering ARIMA models in Stata. This session will guide you from the theoretical underpinnings of time series analysis to practical forecasting applications. We will explore why past performance is often considered the best predictor of future performance, a core concept in time series forecasting. Standard regression methods like OLS, or ordinary least squares, assume that observations are independent, like strangers in a crowd. This holds for cross-sectional data. However, time series data points are like siblings. They are related. Today's value often depends on yesterday's value. This relationship is called autocorrelation. Ignoring this memory or autocorrelation violates a key OLS assumption, leading to biased standard errors and making our forecasts unreliable. Think of daily temperature. The temperature today is highly dependent on the temperature yesterday. You can't just shuffle the days and expect the data to make sense, which you could do with a survey of 100 different people's heights. So how do we properly model this family resemblance in our data? This is where the ARIMA model comes in, following a structured approach known as the Box-Jenkins methodology. The Box-Jenkins methodology is an iterative, four-step process for building ARIMA models. The first step is identification, where we check for stationarity and use tools like the ACF and PACF to determine the model's parameters, P, D, and Q. Next is estimation, where we fit the chosen ARIMA model to the data, typically using MLE, or maximum likelihood estimation. Then comes diagnostic checking. Here, we verify if the model is adequate by checking if the residuals are white noise and if the model is stable. Finally, if the model passes the diagnostics, we proceed to forecasting to predict future values. If diagnostics fail, we must return to the identification step and refine our model. For setting up your data and visualization, commands like tsset, tsline, AC, and PAC are essential. Tsset is the most critical first step. For estimation, Stata provides the ARIMA command, which uses MLE to fit the model parameters. After estimation, we use post-estimation commands like STAT-AROOTS to check model stability and STAT-IC to compare models using criteria like AIC or BIC. Finally, for forecasting, the predict command generates future values, and tsappend can be used to extend the dataset to hold these forecasts. Stata's time series operators handle gaps automatically. A typical workflow is tset your time variable, tsline your data to check for trends, use AC and PAC to identify P and Q, ARIMA to estimate, STAT-AROOTS to check stability, and finally, predict to forecast. You cannot run any ARIMA command without first defining the time variable using tsset. It is the gatekeeper of time series analysis in Stata. The AR component, which stands for autoregressive, is the momentum part. It uses past values of the variable itself to predict the current value. The parameter P denotes the number of lagged dependent variables, or lags of Y. The I stands for integrated, which is the trend removal part. It involves differencing the data to make it stationary. The parameter D is the number of times the data is differenced, or the difference count. Finally, the MA component, or moving average, is the shock recovery part. It models the error term as a linear combination of past error terms. The parameter Q represents the number of lagged forecast errors, or lags of the error term, epsilon. An ARIMA 111 model for monthly inflation means we predict this month's inflation using last month's inflation, P equals 1, after accounting for the trend by differencing once, D equals 1, and also considering the shock or error from last month's forecast, Q equals 1. The I for integrated is crucial because ARIMA models rely on a key assumption about the data, stationarity. Let's explore what that means. A time series is covariant stationary if its statistical properties, specifically its mean and variance, do not change over time. Visually, a stationary series will fluctuate around a constant mean and have a constant band of variance. A non-stationary series, on the other hand, often exhibits a clear trend, changing mean, or its volatility changes over time, changing variance. ARIMA estimation requires the data to be stationary. If your data has a trend, you must apply differencing, the D in ARIMA, to remove it and achieve stationarity. For example, a country's GDP over 50 years is typically non-stationary because it trends upwards. To model it with ARIMA, we would first take the difference, which would represent the GDP growth rate. This growth rate series is much more likely to be stationary. Once we have a stationary series and estimate our model, how do we interpret the coefficients we get? The AR coefficients, denoted by phi, represent momentum or stickiness. A positive AR means that a high value yesterday is likely to be followed by a high value today, such as in the case of sticky wages. These coefficients capture the memory of the system. The MA coefficients, or theta, represent shock absorption. They tell us how the system responds to unexpected external shocks, like strikes or oil price fluctuations. They indicate whether the effects of a shock dissipate quickly or lead to oscillations. The magnitude of the AR coefficient is directly related to persistence. A high AR value means shocks have a long memory and die out slowly. Conversely, a low AR value indicates that shocks die out quickly. A critical point is the concept of a unit root. If the AR coefficient is 1, the shock is considered permanent and will never die out. Before any analysis, you must tell Stata which variable represents time and what the frequency of your data is. This is done with the tsset command. First, you often need to create a proper time variable. Stata has functions like tm for monthly data, tq for quarterly, and so on. In this example, generate t equals tm 2000m1 plus n-1 creates a monthly time variable starting in January 2000. Here, tm 2000m1 is the creation function for monthly dates, 2000m1 is the display format, and n-1 accounts for the observation number to ensure the time variable is sequential. After creating and formatting the variable using format t%tm, you declare it using tsset. Stata now understands the data's time structure. Note the various frequency formats on the right, %ty for yearly, %tq for quarterly, %tm for monthly, and %td for daily. A useful tip, use the delta option with tsset if your data has gaps. Once the data is properly set up, we can move on to estimating the model itself. Stata offers two main ways to specify your ARIMA model. Method A uses explicit lags, such as ARIMA Y, R12 Ma1, which is useful when you need to include specific non-consecutive lags, for example, for seasonal effects. Method B is the ARIMA shorthand, like ARIMA Y, ARIMA 211, which is more common and convenient for standard models with consecutive lags. A key tip to remember is that R13 includes lags 1, 2, and 3, while R13 includes lags 1 and 3 only, skipping 2. The shorthand ARIMA PDQ automatically assumes consecutive lags. Additionally, there are important options like VCE robust for calculating robust standard errors to handle heteroscedasticity, and technique robust allows you to specify the optimization algorithm used for finding the maximum likelihood estimates. Our case study involves forecasting the U.S. Wholesale Price Index, or WPI, using quarterly data. The first step is always to visualize the data. We load the data, tsset the time variable, and then use tsline to plot the series. The plot immediately reveals a strong upward trend. The mean is clearly increasing over time. This visual diagnosis tells us the series is non-stationary and will require differencing before we can model it with ARIMA. We also need to check for changing variance, which might require a log transformation, and seasonality, which would point to a seasonal ARIMA model. We will estimate an ARIMA 111 model. This includes one AR term, one level of differencing, and one MA term. Stata's time series operators make this easy. We can use d before a variable name to difference it directly within the ARIMA command. Here, we also apply a log transformation, ln_WPI, to stabilize the variance. The command ARIMA d ln_WPI, AR1, MA1, explicitly models the first difference of the log of WPI. Alternatively, and more conveniently, we can use the shorthand ARIMA ln_WPI, ARIMA 111. Stata understands that the 1 in the middle position for D means it should perform one level of differencing on ln_WPI internally. The D operator calculates yt minus 1. The L operator, not used here but related, simply gives the lagged value, yt minus 1. These operators prevent us from having to manually create new variables for lags and differences, which is very efficient. After running the command, Stata provides an output table. Let's learn how to interpret it. When interpreting the Stata output, we first look at the model fit, indicated by the log likelihood. This value is used in information criteria like AIC and BIC to compare different models. Next, check the significance of the coefficients. The p greater than z column contains the p-values. A value less than 0.05 typically indicates that the coefficient is statistically significant. The coefficients themselves are listed. Here, the AR1 coefficient is 0.874, and the MA1 is negative 0.412. Note that the output shows the MA coefficient with an opposite sign in some conventions. Finally, sigma represents the standard deviation of the residuals, which is a measure of the model's overall volatility or prediction error. On the right, you can see a checklist for interpreting the output, reminding us to check p-values, model convergence, and the acceptability of error variance, sigma. After estimation, we must check for model stability. An ARIMA model is stable if the inverse roots of its AR and MA polynomials lie inside the unit circle. In Stata, the STAT-A-roots command performs this check and provides a helpful visualization. If all the dots, eigenvalues, are inside the circle, the model is stable and satisfies the stability condition. This means that the effect of any shock will eventually die out. If any root is on or outside the circle, the model is unstable. This could mean the series is non-stationary, needs more differencing, or the model is misspecified, too many lags. If you estimate an AR1 model and the coefficient is 1.1, the root will be outside the unit circle. This indicates an explosive, non-stationary process. The correct action would be to go back and difference the data. Our model has passed the diagnostic checks, so we can now proceed to the final step, forecasting. The forecasting process involves two main commands. First, we use the tsAppend command to extend the dataset by adding new time periods for which we want forecasts. For example, tsAppend, add 10, would add 10 new quarters. Second, the predict command generates the forecast values. The option "y" is crucial here, as it tells Stata to produce the forecast in the original scale of the dependent variable, automatically reversing any differencing or transformations that were applied during model estimation. This is known as a dynamic forecast, where predicted values are used to predict subsequent values. A key constraint of ARIMA forecasting, illustrated by the diminishing reliability over the 20% forecast horizon compared to the 80% historical data, is that accuracy tends to degrade over longer forecast horizons as uncertainty accumulates. Thank you for joining this session on ARIMA models in Stata. I hope this journey into econometrics has been insightful. We've covered the crucial steps. First, to visualize your data with tsset.